Spectre, breaking and fixing microarchitectural vulnerabilities by formal analysis. So the main motivation behind this work are basically the family of Spectre attack. A couple of years ago, researchers has identified problems that lead to programs that were considered secure, and for secure here, I mean free of side channel, to be non-secure when they're actually executed on a real hardware due to some low-level optimization like out-of-order execution and speculation. So this is a slight modified version of the original Spectre attack. So suppose that we have a program that has two arrays, A and B. It reads from some location in memory the size of the first array, and then it checks if the register R0 is less than the size of the array. So this register R0 is controlled by the attacker and is a parameter to this function. Then if this condition pass, the program reads the array in position R0, that's basically the index inside the array A, it gets a value, and then use this value to index a second array that is the array B. So now, without speculation, this program can have two different behavior. If the attacker provides a value that is less than the size of the array, this program will access the memory in two different locations. In the location R0, well, in the location depending on R0, that is the index used for this, and then in the location in a location that depends on the content of A in R0, right? That is the index basically used for the second memory access. So in the other case, in the case that the attacker provides a value that is greater or equal than R1, there will be no memory access. So now suppose that the attacker is able to monitor the cache and these memory access can leak information. If we assume that the register R0 is new by the attacker and also the content of the registers of the arrays A and B are new by the attacker, then this program will be considered secure. In fact, usually we say that this program respects the constant time policy because all control flow operation, this branch basically, and all memory access are only performed using public information. The register R0, the size of the first array, the register R0 here again, and the content of the array A, assuming that this array is public. Now, what happens when we execute this program in speculation? Well, even if the attacker provides a value for R0 that is greater than R1, the processor may decide to speculatively execute this branch. So now this load will load from the array A in position R0, but this index now is larger than the array A, so this will lead to a buffer overread. That means we read out of bound of this array. Now, maybe after the array A, we have a cryptographic key that now it's loaded into the register R2, and we use this register to index the array B. This will basically leak through the side channel, maybe a data cache side channel, the value of R0 that has been read basically out of bound. So programs that were considered secure are potentially insecure or affected by side channel when executed in speculation. And there have been many variations of Spectre, each one using different type of prediction of modern processor, like Spectre V1 that uses branch predictor, Spectre V2 and Spectre V3, where the processor predicts the return or indirect jump address, basically predicts the control flow, a Spectre V4, where the processor predicts the dependencies between load and store. So the goal of this work is to provide a foundational model for out-of-order execution and speculation. And our goal is basically to be general enough that we can capture all possible variants of Spectre. The model is built on top of 5 main ingredients. We define an abstract micro-operation language that allows us to be machine independent. Basically, instructions have to be transformed this abstract micro-operation that allow us to be architectural independent and also allow us to model the fact that in a modern processor, instructions are not executed atomically. Then side channels are modeled via observation. These observations are a sort of leakage function that over-approximate which information of the processor can be leaked when we execute some micro operation. Then the verification condition are basically inspired by non-interference. The intuition here is that an attacker should not distinguish more state in a processor with speculation than states that can be distinguished in a processor without speculation. Then we define an out-of-order semantic for the microinstructions. And finally, we define a liberal speculative semantics that allow processor to guess value, to predict values for the microoperation, and allow basically to model speculation. Of course, finally, we use basically this model to investigate and to analyze existing vulnerabilities. We actually found also new vulnerability and to verify soundness of countermeasure. So let's start with this machine-independent language. So the microoperation works basically operates over three types of resources. We have registers that are basically internal of the processor, like register. These are basically the general purpose registers of the processor. Then we have the program counter that is a special resource that basically affect the control flow of an application. And then we have a memory that is treated in a special way, since accessing the memory, like writing into memory or reading from memory, can send information to the memory subsystem and can leak information to the data cache that are basically the side channel that we assume are accessible by the attacker. So now any microoperation here is uniquely identified by a name, T1, T2, T3, T4, T5, T6, and T7 in this example, that are basically totally ordered. These names basically identify the program order of the microoperation. And we have three different microstructures. So the first one are internal operation. For example, this instruction set the name T1, or at least set the value of this microoperation with a constant, that is the constant R1. Or this microoperation T3 computes basically the sum of the result of a previous microoperation T2 with 1. So it just increased basically T2 by 1. Or this other example, the microoperation T6 increased basically the result of the microoperation T5 by 4. Then we can load the resource. In this example, T2 is a microoperation that load from the register file the entry that has been indexed by the previous microoperation T1. So basically in T1, we set the constant, that is the identifier of the register, of the first register of the machine. And then T2 will read from this register, basically, from the register file from this address. Of course, we can also read the program counter and we can read memory. And finally, the last microinstruction is a store. So we can modify a resource. In this case, we store into the register file into the position addressed by the microoperation T1, that is the register 1, the value computed by the microinstruction T3, that is basically this increased by 1. So this is, for example, the translation of the instruction that increased the register R1 by 1. And notice that there are two streams of microinstruction. The first one is the one that allows us to read the register, increase this by 1, and store again the result inside the register file. The second stream that is independent of the first one is the stream that increases the program counter, right? Whenever you execute an instruction, you also increase your program counter. In the case of 32-bit architecture, you probably increase this by 4. So this read the program counter, increase by 4, and store the program counter. Now, each microinstruction can be conditionally executed as basically a guard. When we omit the guard, it means that the guard is basically tautologically true. But some microoperation can have a guard. That means this microinstruction has to be executed only if the guard can be evaluated to true. So suppose that we want to model a conditional branch that jump to the address A if the flag Z hold. Well, we will read the flag Z, we will compare this with 1, and then we decide to modify the program counter with the value A. So we store A into the program counter if the previous comparison result to true. Otherwise, if the previous comparison result to false, we just increase the program counter by 4. Now, we don't define the translation for different microarchitecture, but basically the intuition is that if you want to model a specific microarchitecture like x86, ARM, RISC-V, MIPS, you need to basically define a function translate. They take an address that is basically the address of the instruction in the program. It takes the last name of the last micro instruction executed until now and generate a set of micro instructions that are basically the decoding of this instruction, or basically is the transpilation of this instruction. Okay. Now, the second ingredient is the model, or how we model the side channel. So as I said before, we don't explicitly model side channel, like we don't explicitly model the cache hierarchy, we don't explicitly model the cache replacement policy, and so on and so forth. Instead, we basically assume a timing insensitive trace-driven attack. That means we assume that the attacker can somehow discover the sequence of memory operation performed by the victim, but not exactly when they happen. So that's why we call this a time insensitive trace-driven attack. So the attacker can use maybe a prime plus probe attack or a flash reload attack. We abstract from this and we just say, well, in the worst case, the attacker will be able to discover the sequence of memory operation and the address that has been accessed by the application. So for this reason, we have basically 4 observations that represent possible leakage of our micro operation. We have the empty observation that happen whenever we execute an internal operation, we read the register, or we store a register. Then we have data load of an address or data store of an address that leaks the address that has been loaded or stored into the data memory. And then, assuming that the attacker can also observe the instruction cache, we have a final observation that instruction load A that leak the address of the program counter whenever the processor fetch the next instruction, since fetching an instruction can affect the instruction fetch. So the goal here is to define a model, right, and verify properties of this model, or at least verify property of software accordingly to this model. And we basically focus on 2 main properties. The first property is a functional property that say that the model that we are defining is functionally correct. So it implement correctly is the sequential processor. And the minimum requirement that we pose on this model is memory consistency. So we introduce a reference sequential model. So this reference model execute every instruction in order, basically. And then we ask that for a refined model, for example, a model that implement out-of-order execution, or a model that provide speculative execution, for every trace pi of the refined model, there must exist a trace raw of the reference model, such that for every address A, the sequence of values that we store in the address A are the same in the refined model and the reference model. So this is often called memory consistency. And that means that in the refined model, we allow to arbitrarily reorder loads, we allow to arbitrarily remove or add loads or internal operation or register operation, but the sequence of memory store for the same address has to be preserved. So for example, supposing that this is a trace in the sequential model, where we save X into the address A, then we save Y into the address B, then Z into the address A, and then W into the address B, we will allow, or we will consider memory consistent a model that swap these 2 store, since they write into different address, this write into the address B and this write into the address A. So we allow this swap, or we will allow to introduce additional memory load or remove memory load, but we will not allow to reorder, for example, these 2 memory store, since the first one write X into A and the second one write Z into A. If we reorder these 2, we will get a wrong pipeline. So this means that no matter what your pipeline does, right, you need at least to ensure this property to guarantee that your processor work. So this is not really a security property, is more a functional property to justify that your model is meaningful or that your pipeline is meaningful. Then, for a security point of view, we would like to guarantee what we call conditional non-interference. So the intuition here is that if we start from a pair of states, sigma 1 and sigma 2, that are non-interferent in the sequential model, in the reference model, and for non-interferent here, it means that for every trace rho 1 that starts from sigma 1, there is another trace rho 2 that starts from sigma 2 that is observational equivalent. So that basically has the same footprint on the side channel. So if two states affect the side channel in the same way, are non-interferent in the sequential model, then these two states must also be, or they should also be, non-interferent in the out of order or speculative model. And this will show that basically your program or your pipeline does not introduce any side channel. Of course, we know that this is in general will not be possible, since we know that in the case of Spectre attack, we will violate this property. So this also means that in the refined model, for example, in the model with speculation or in the out of order model, we will allow to completely change the trace. We will allow also to introduce a new transition in the trace. But if the original two states were indistinguishable, then if there is a trace with this observation starting from sigma 1, there must be a trace also with this other observation starting from sigma 2. Okay, we can now start to define the out of order semantic of this language. So each instruction goes through 4 states during its life cycle, and the state consists of 4 main components. So the first component is I, that is the set of microinstructions that has been done or have to be executed. So these are basically like is the history of all microinstructions that has been put in flight in the pipeline. So initially, when we execute an instruction, we first take the instruction, we translate the instruction to many microinstructions, and we put all these microinstructions in the decode phase. That means they are basically inside the set I. Then when we execute any instruction, when we execute a microinstruction, basically, we set a value for the identifier of the microinstruction. For example, if the microinstruction T5 consists of the constant 5, executing this will set 5 into a partial store that is called S for the name T5. Okay? So the majority of instruction, microinstruction ends here. They have only 2 states. They start from the decode and then they execute, at least in the out of order semantics. But there are 2 types of instructions, memory store and program counter store, that need to do an additional step. So in modern microprocessor, store are performed usually in 2 steps. You first execute the memory store. This memory store is added inside the reorder buffer, and only later on the reorder buffer is sent to the memory. This is especially needed in case of speculation because you want to execute load in speculation, but you cannot send them to the memory subsystem until you have retired the instruction, because you cannot roll back what happened in the memory subsystem. Okay? So similarly, when we modify the program counter, this should have 2 effects. We first modify the program counter, so we go from decoded to executed, and then later on, we need to fetch the new instruction and add many new micro instructions in flight, basically. So to fetch basically the new instruction. So for this reason, we have other 2 states that are called C and F, like other 2 components of the state. C is the set of committed microinstruction to the memory store, and F is the set of fetched microinstruction that represent PC store. So I can now define the semantic of a single microinstruction before composing them and give the reduction semantic. So the semantic of an internal operation is relatively simple. So remember that an internal operation basically consists of an expression that can refer to other microinstructions. For example, this E may be T1 plus T2. And the semantics say, well, assuming that in the state sigma, you can evaluate the expression E, that means all names that are in E are defined in the state sigma, so you already have executed all depending microoperation, then the result of this microoperation is equal to evaluation of the expression, and we have an empty observation because this is an internal operation in the pipeline. Then, whenever we perform a store, the semantic is basically the same. Assuming that you know the value that you want to store, and assume that you already have evaluated the address where you want to store, then the semantic of the store is just basically the value that you want to store. And also this microinstruction has not direct observation. The reason is that this is only the execution. Later on, we will see the observation when the store is actually committed to the main memory. The semantic of load is slightly more complicated. So when you execute the load, you first need to identify what is the last store that has modified the same address that is assessed by the load. And this is complicated since instructions are executed out of order. And the dependency cannot be computed statically since the address are computed dynamically, right, by other instructions. So for solving this problem, we introduce a predicate that is called store active that I will give you by example. I will not give you the exact definition of this, that take a state and identify for a load T what are all the possible stores that may override the address loaded by the load in address T. Now, this set can be large, but when this set becomes a singleton, it means that we were able to identify the last store from where we need to fetch the value. So you can execute a load only when the store active are become a singleton, only when you have resolved the dependency of the load. In this case, assuming that you know the address and assuming that you know the value that has been stored, well, the semantic of the load is just equivalent to the value that has been stored by the single dependency that we have identified using the store active. Now, regarding the observation of a load, you can have two different observations. If the store from where the load is taking the value has already been committed, it means that the store is not anymore in the store buffer. It means the store has been sent to the memory subsystem, and that means that the processor has to access again the memory subsystem to fetch the value. So in this case, we will observe a data load of the address that we are loading. Otherwise, if the dependent store has not been committed, it means that the store is still inside the reorder buffer. Then we can model what is called a data forward. That means the load directly fetch the value from the store buffer without having actually to perform any operation to the memory subsystem. This is basically a silent operation because there is no access to the cache. In this case, we have an empty observation. So regarding the store active, so this is basically what allows us to compute dynamically the dependency of loads. And I use an example to explain basically the behavior of store active. So suppose that we have a system here, a program with three stores, T12, T22, and T32. These stores, they all come before the load in named the T42. Now, these four microinstructions are the four microinstructions that identify the address where these stores are storing or from where this load is loaded. So the first store into the address computed by the microoperation T11. The second store, T22, stores into the address computed by T21, and so on and so forth. So now suppose that we are in a state where we know we have resolved the value of T11 and T41. So we know that this load is reading from the address 1, and this store is storing into the address 1. In this stage, we have no idea where this store will go to write, and for this reason, all these stores will be in the store active of the load. That means the load has to wait because the dependencies have not been resolved. Now, suppose that we discover or we execute the instruction T21, then we know that the store 22 is not writing into the same address of the load, and we can remove this store from the store active. Now, suppose that later on, we also execute the instruction T31, we get to know that this value is 1. That means that the instruction T32 is overriding the value of the instruction T12. That means we don't need to wait T12. At this point, we identified the single store active of the load. That means that the load, T42, can be executed as soon as T32 is ready. We don't need to wait the execution of T22 and the execution of T12. So this allows to define basically the out of order semantics. So we have basically three semantic rules that reuse the semantic of microoperation that we have discussed before. So the first rule represents this transition, the execution of an instruction. Assuming that we have an instruction in the pipeline, that this instruction has not been executed before, so its value is undefined in the partial store. Assuming that the condition of the instruction hold, that the guard of the instruction hold, this is an instruction that has to be executed. Assuming that the semantic of the microinstruction give us the value v and the observation L, then we can perform a transition, observe the observation L, and modify the partial store appending to the value t the value v. And then for memory store, we have this additional rule for commit. Assuming that we have a memory store in the list of instructions, that this has been executed before, that has not been already committed, and that all previous stores in the same address have been already committed. So we can execute store out of order, but when we send them to the memory subsystem, we need to ensure that for the same address, they are ordered. Otherwise, we will break memory consistency. So at this point, we will observe a data store of the address of the store, basically, and we will extend the committed part of the state with the name t. And for fetch, the story is similar. So assuming that we have a program counter update, that this program counter changed the program counter to the value a, so this is the new address of the program counter. Supposing that this instruction has not been already fetched, and supposing that all previous program counter update has been already fetched, then we can observe an instruction load at the address a, that is the new address of the instruction, and we can extend the list of fetched instruction with an MT, and we also can extend the list of microinstruction with the translation of the instruction that is currently pointed by the program counter. Okay, so this basically will add many microinstruction in the set I prime, and these are all in basically the state decoded. So this out of order semantic is quite general, right? It's completely non-deterministic. We don't restrict the scheduling, right? We don't restrict like the order of evaluation, the depth basically of how long can be postponed an instruction. But we prove that even if it's so liberal, we have memory consistency. And this is a good news because basically any out of order, any realistic out of order semantics will actually have less traces, or at least will have the traces included into the trace of this semantic. And since this is already memory consistent, then any other out of order semantic that is just obtained by restricting these semantics will also be memory consistent. But surprisingly, we cannot prove conditional or interference. So I show a counter example for this, and we actually have found this vulnerability by actually trying to prove conditional or interferent for the out of order semantic. So suppose that we have a program here. This program reads from the constant address B1 and write this into the register R1. Then if the flag Z hold, it moves the register R1 into the register R2, and then stores the register R2 into the constant address B2. Now, in the in-order semantics, I don't care for now about the program counter update, but in the in-order semantics, there are only two observations that affect the data cache. There is a memory load here, and there is a memory store here. So we have a load from B1 followed by a store in B2. Since this is in order, we will always observe these two observations, basically these two operations to the memory subsystem. There will be other micro operations here that can be executed or not, but this will always happen. So the observation to the memory subsystem that affect the memory subsystem will always be the same independently of the code, the value in the memory, the values of the registers, the value of the flag Z. Now, suppose that we execute the same program in the out of order semantics. Suppose that the flag Z hold. Well, if the flag Z hold, it means that we need to update the register R2 at this point with the value of the register R1. That also means that this store has to wait this load. So if the flag Z hold, again, the attacker will always observe the same sequence of observation. First the load from B1, and then the storing to B2. But if the flag Z does not hold, then this condition does not hold, and this operation should not be executed. This means that there is no reason for this load to wait neither this operation or this load. And that also means that this store, the store of the register R2 into the location B2, can be executed in out of order as soon as we resolve the fact that this flag Z does not hold. We don't need to wait this load. So if the attacker observes that first there is a store into B2 and then there is a load from B1, the attacker immediately discovers the flag Z. That means a bit of a secret is leaked to the attacker. So it means that the system has a side channel. So on top of the out of order semantic, we introduce a speculative semantics. And well, for the speculative semantic, we need two additional components in the state. One is P and the other one is delta. The intuition here is that we will allow the processor to arbitrarily guess, non-deterministically guess, values of micro-operation. And the micro-operation that are predicted by the processor will be keep track inside this set P, the keep track basically of predicted micro-operation. And then whenever we execute an instruction in speculation, in delta, we will save a snapshot of the state of the dependency of the microinstruction, so that later on we can decide if this execution was correct or not. If the execution was correct, we can retire the instruction. If the execution was wrong, we can perform a rollback. I will show the semantic by example, okay? So in the first case is prediction. Suppose that we have this program. This is similar to the conditional branch that I presented before. We load the register Z, we compare this with 1. If this hold, we jump to the address A. Otherwise, we increase the program counter by 4. And additionally, just to make the things more interesting, we also store the value of the flag Z inside the memory in position 16. Now, initially, all instructions, all these 6 instructions are in the state decoded. And the rules say, well, at any point, the processor can decide to take an arbitrary instructions that has to be decoded, that has not been executed, and just basically flip a coin and generate an arbitrary value for that instruction. So in this case, basically, we'll extend the storage with an arbitrary value for this instruction that has been predicted, and extend the prediction set with this instruction that has just been predicted. For example, the processor here may just predict that the value of the micro instruction T2, that is the one that performed the comparison, is 0 by just flipping a coin. This semantic is totally non-deterministic, right? So the processor can also decide to flip the other side of the coin and get the value 1 for the same microstructure. So then suppose that we do some step that I'm not detailing here. So we, for example, execute actually this load of the register of the flag Z, and we get to discover that this value is 1. And we also load the program, read the program counter, let's say it's 32. At this point, we already observed that this prediction is wrong, but the semantic does not force the processor to immediately roll back the value. Again, this is totally non-deterministic in our semantics. So at this point, the processor may decide to execute some instruction in speculation. So the rule basically reuse the out of order semantic. It say, well, if in this state you are able to execute this instruction because the flag Z here is false and the program counter is equal to 32, so if you are able to execute this instruction, you can also execute this instruction in speculation. So this will set this instruction as a 36. But when you execute this, you need also to save the dependency, all instructions that are needed to compute this value. So in this case, we need to save that when we execute this instruction, the value of the flag of this T2 was 0, and the value of the program counter was 32. Similarly, we can use the same rule to execute this memory store, right? So this only depends on this other instruction that was 1. So we can execute this. We can execute this micro operation, set the value to 1 according to the out of order semantic in speculation, and save basically the dependency for later on check if this speculation was correct or not. Then at some point, we allow, again, non-deterministically, the processor to fix a prediction. And the rules say, well, if you have predicted some micro operation, you can remove this micro operation from the state, check what happened in the out of order semantic, and then perform the same execution in the speculative semantic to correct your prediction. In this case, you will remove T from the prediction, and again, you will save the dependency of this execution. So in this case, right, from this state, we may decide to correct this prediction. That means we execute this instruction, since this check if the micro operation T1 is equal to 1, this is true, this will perform a step and will set this micro operation to 1, setting basically the dependency equal to 1, because this was the only dependency that we have. So this allows basically the processor to correct mispredictions. Then we can fetch instructions in speculation. So we have this instruction that was executed speculatively, and the semantics say, well, if in a state you are able to execute a fetch in out of order, well, you can do the same fetch in speculation, but for all instruction that you have added to the pipeline, you need to add the dependency with the instruction that has generated this fetch, so that later on, in case of rollback, we can remove this instruction from the pipeline. So in this case, we will generate maybe 2 instructions, and we will save that these 2 depends on the fact that this micro instruction was set to 36. At some point, the processor may retire instructions. That means it check a speculated instruction and check if all the dependency of this instruction has already been resolved, and if the current state of the pipeline is consistent with the dependency that have been saved before, then the instruction can be removed from delta. That means the instruction can be retired. So in this case, we have this instruction that was speculated, and when we have executed this speculation, we saved the fact that this micro operation was 1. Now, since this operation is actually 1, we can retire this other micro instruction and remove this from delta, so that now we can basically save its value in the state. And of course, in the case that you have a mispredicted value, or you have done a miss that lead to a mis-speculation, you can roll back instruction. In this case, again, supposing that you have a state, and in this state now is not consistent anymore with the dependency that you have saved and when you have executed T. So in this case, for example, when we have executed this instruction 36, this instruction, we have saved the dependency that this instruction was 0, while actually it's 1. So you can roll back this instruction. That means you remove all side effects of this instruction from the pipeline. You remove the instruction from the state, you remove from the fetch, you remove from everything that has been predicted, and also you remove all other instruction that has been generated from this one, right? So in this case, we will remove T1 prime and T2 prime, since they were depending on this instruction that we are rolled back. Finally, again, reusing the out of order semantic, we say, if the out of order semantic can perform a commit, also the speculative semantic can perform a commit, in this case of this memory store, but this is only possible if the instruction has already been retired. And this is because we cannot perform memory commit in speculation, since for the pipeline will not be possible to roll back events into the main memory. Okay, so commit can only be done for retired instruction, while, for example, fetching here is allowed in speculation because we can roll back the effect of the fetch inside the pipeline. So this gives a quite liberal semantics because we can predict arbitrary values. We leave the processor to free to roll back misprediction immediately, or keep going and perform a nested misprediction and only later on to correct this misprediction. It also allows basically to recover only partial of misprediction in the case that a prediction of the processor allow to speculate something correctly and something that's wrongly. The processor here is allowed to only roll back part of the state instead of roll back the whole state. So even if this semantic is, I would say, wild because it allows basically the processor to predict arbitrary values, we can still prove memory consistency for this general semantic. And again, this is a good news because for an actual processor, the actual semantics will generate a subset of the trace of this general semantics. And that means we have memory consistency for any semantic that is obtained by limiting the non-determinism of this general semantic. So now, how do you verify, how do you study properties of an actual microarchitecture? Because this general semantic is too general, right? So in a real processor, we don't just guess arbitrary values from microstructures. Well, first you need to define the translation for your instruction set architecture to the microoperation. And then you have to reduce the non-determinism of this general semantics to model basically the peculiarities of your microarchitecture. For example, you may limit the microoperation scheduling to represent the limited size for the store buffer. Or you may limit the depth of speculation. Or you may limit which microoperation can be predicted and which value can be predicted. So in practice, usually, we define a side condition that say whenever the processor predicts a value, it needs to satisfy a prediction predicate that is specific for an architecture. So this predicate takes a state of the system and returns a partial function, whereas domain are the name that can be predicted and codomain are the possible values that can be predicted. And this is used for emulate, for example, prediction tables of real CPU. So for example, we can define this prediction function to emulate, to allow only prediction of, to allow only branch prediction. That is what calls Spectre PHT. In this case, the prediction set will be a parser function that allow to map T to V for every T such that there is a program counter store whose condition C prime depends on the name T. So we basically only allow to predict the names that affect the condition of program counter store. So since the condition of the program counter store are the one that affect the branch predictor. And well, we modeled this microarchitecture, for example, and then we studied that some countermeasures are sound. For example, we studied that Intel implicit serialization is sound. Or we can model Spectre STL. So this is a variation of Spectre where the processor predicts that the memory store will not affect a subsequent memory load. And the strategy is basically is to limit the prediction by saying that, well, you can predict the address of an arbitrary store to be different than the address of a subsequent store. So that's basically the prediction. So I say you can predict a name TA to be set to a value A, assuming that there is a load and there is a store, and this store use the address TA, and the address that you can predict has to be different than the address of the load to mimic basically the store bypass of Spectre STL. But we also identified a complete symmetric policy where the processor, instead of predicting that the memory store may not affect a subsequent memory load, may actually predict the opposite, may predict an alias. So this was not discovered in the wild before, but we assumed that this was possible, and we identified that this is actually a potential vulnerability. So for concluding, so we define a semantic that is general enough to cover all possible existing variants of Spectre, and we use this semantic to both study these variants and to analyze the soundness of existing countermeasures. We also identified 3 different variants of Spectre using this semantic, basically, by doing proof using the semantics. And in particular, we have discovered that even without speculation, just executing out of order may introduce additional side channel. For this specific case, we are also introduce a new policy that is called out of order aware constant time, and we verified that this is sound, that if your software implement out of order aware constant time, then there is no additional leakage due to out of order execution. And that's all. Any question?
Thank you very much, Roberto. We just listened to a UK SBS seminar from Roberto Guanciale, who is an associate professor at KTH, Royal Institute of Technology in Stockholm. As you have seen, his research is very much on formal verification of code and separation kernels, apparently. And definitely we welcome and thank you again for your additional input on your work in Spectre, breaking and fixing microarchitectural vulnerabilities in biformal analysis. So, sorry for this late introduction, which we missed, but we were really thrilled to hear from you. Now, we have some questions from the chat. Yeah, let's remember those are recorded questions. So
yes. So in this, by the way, yes. Yeah. So in this work, we only focus on Spectre variants. So there is a difference between Spectre and Meltdown, because in case of Meltdown, it's well, there is basically the processor is not enforcing a security policy, while all the variants of Spectre is basically the speculation that introduced this. So for Spectre v3 here, I don't mean Meltdown. Here I classify differently V2 and V3. The V2, I mean basically the one where there is where the processor predict the indirect jump. A Spectre v3 is when the processor basically predict return address of a function call. So this there are different topologies of Spectre, and in basically here I mean basically the one where the processor can predict the return address of a function call.
Yep. Sorry, can I just say a quick thing? So in the work that I just referred to, it was they were saying that they're referring to this V3, they're referring to it as version 5, and in the original work they were referring to Meltdown as the V3 Spectre. It's just I was just confused with that. Thank you.
Yeah. But in general, I mean, this was basically an introduction of different types of Spectre. So the goal here, we believe that at least until now, we were able to model all existing variants of Spectre, basically. But Meltdown is a different ball game, right? So we cannot model Meltdown with this semantics, since there is no model of memory protection in the model. So everything that has to deal with memory protection is out of scope here.
Yeah, thanks for the question. Does anybody else have a question for Roberto? Well, in the meanwhile, that you may need to think about it, I have some questions myself. So one is actually, how do you relate to other works that try to formalize similar aspects for Spectre? And I'm particularly speaking about the constant time foundation for the new Spectre era, paper from Caoligi and other authors, where they very much, let's say, cover it. Probably it's a work the same time as yours. So
yeah, this is quite interesting because we published basically the paper close to the same time, and many things were close to each other. So it's interesting to see like how we found similar solution for the same problem. I think there is a main difference in the semantic. So they have an explicit reorder buffer.
Right.
And we don't have an explicit reorder buffer. And this allows us to be slightly more abstract. For example, we allow some additional reorder behavior. For example, we allow store to be on different address to be executed in any order, while the store in that work are basically satisfy a total stall order. That means the store are totally ordered when they're sent to the memory. And this is not always the case, basically, on a modern processor. Another thing that we allow is basically for the same reason, like we can model this vulnerability here, because we allow this load to come before this store. In the case that, and this is not allowed also in that case, because even if you have out of order execution, since there is a total store order, you cannot reorder this store before this load, basically. And but then they've done much more work, for example, on tooling. For example, they have Pitchfork that allow actually to check code. Currently, we don't have a tool for doing the analysis, right?
Yeah,
for now, we only have a theoretical result.
Yeah, you anticipated one of my questions. So yeah, thanks again for clarifying that out. Because I remember that you mentioned in the paper as a future extension of InSpectre, probably a tool would have been a nice thing to have. I don't know if I may, another question. I don't see.
Can I ask a question?
Yeah.
Yeah.
Maybe I missed something. So for the solutions you propose, is that a hardware-based solution, or is
it depends, right? So we analyze many different countermeasures, right? So these are basically specific. For example, the case of fence, well, this is basically the standard fence, right? And we show that, well, fence is sound, but you need the proof, right? That's many work didn't make a proof of this. So, but for example, implicit serialization is not really a fence, right? It's a trick implemented by Intel, right, that allow you to introduce a data dependency that prevent this speculation window. This is also like a software solution, and we prove that, well, we don't have a formal proof. Let's say we have a formal analysis because we don't have a complete formal proof that implicit serialization is sound. And Red Pauline is this countermeasure provided by Google to basically cage the speculation of control flow, so that in the case that there is a mis-speculation, this is directed to a while loop that performs NOP, and so there is no leakage. And also in that case, this is a software construction, and we verify that this general software construction is sound, basically. In the case of ARM SSB, this is instead an hardware feature. So we basically restricted the non-determinism of this semantic by adding basically the restriction of ARM SSB, and we show that, well, this is enough to prevent basically Spectre before.
Okay, yeah, thank you.
Yeah,
very interesting. And yeah, I also was thinking about when an application, real application in a real architecture, where you don't expect all the instructions to actually be used to do this kind of speculations. So I'm basically speaking about speculation windows. How your work can refer to those, or does it need to be extended to it? How is it could?
So we are working in two areas here. So together with the guys that are working on binary verification in our group, we developed a tool that generate tests, basically, starting from programs, and then try to identify how that is basically the speculation window for single processors. And that's one area, basically. This is more, let's say, validation of the model, right? So that you can say, well, I will, I limit my speculation window to 4 instruction or 2 loads, 1 load or 2 depending load, and so on and so forth. And then this generate, basically, try to find programs and states that violate this assumption, basically, and see if there is a difference on the actual board. And another work that we are starting to do, but we are still like in the early stage, we are modeling this work in an interactive Turing prover. And our goal is then to later on model an open source pipeline like Ariane RISC-V processor, and then actually show a refinement between this abstract model and the actual processor VHDL design, so that we can define an over approximation of the speculation window, but also prove that this over approximation is sound.
Yeah, thank you very much for, yeah, I think it's definitely clarified my question. We also have a question from Martin Berger. Can you please?
Hi, you just mentioned that you wanted to verify this against the Ariane core, but that's an in-order core. Did I?
No, it has some form of speculation. It has, well, okay, it is in order, but it has a speculation, right? So this will be the first step to do to set up our work, basically. So some of this behavior, right, happen even if you don't have out of order, or at least there is a sort of you can, since you have a multi-stage, the pipeline can fetch speculatively accordingly to the branch predictor, and this is enough to actually expose Spectre PhD1. So we not, in this case, basically, we should be able at least to start to set up basically this comparison.
But so you want to go further down to the register transfer level, but is it also interesting to go further up, like to say, okay, these pieces of software, these gadgets are dangerous or not dangerous from your model?
Yes. So one problem that exactly. So one point is that if you take these models, right, it's really hard to prove these properties.
Yes.
Once you say, okay, the architecture is in general non-secure, and this is usually the case in reality, right? Because if you have speculation, you know that if you don't take any defense, in practice, you will not satisfy this conditional interference. So now you are after the problem of analyzing an hyper property to a really, really complicated model, right? Because once you take into account speculation and out of order execution, the traces are really large, right? And that's become really complicated. So what we have done, for example, for this countermeasure here, was to identify a sufficient condition on the in-order semantics that allow us to show that, well, if your software satisfies this in-order condition, so if you can verify this property, that is still an hyper property, but is an hyper property of the in-order semantics, then we can show that conditional interference. And that's basically the strategy. This is basically similar to the strategy that has been used also by the guys of Spectator, right? Where you have, even if you only analyze branch prediction, you can have nested prediction, right? And they show that, well, you don't really need to verify all nested prediction. It's enough that you verify your code against the always mispredicting behavior. And then this should be enough to guarantee that all other possible misprediction will leak less than the always mispredicting behavior. So that's what we are working on.
You said this was a sufficient condition. Is it also necessary?
No, it's not necessary.
Okay. Do you think it's possible or interesting to have a precise characterization in this way at the for an in-order core?
Would be really, would be nice. So we discussed about this. The idea initially was to use a sort of weakest relation generation. Like instead of having a weakest precondition, like start by this condition and try to build the weakest relation for your software that has to be met to guarantee conditional interference. But I don't know. We have not to go really to the far enough to say that this is possible or not. Basically. It would be nice to have basically to have a necessary condition, but I'm not sure that this is super possible.
Thanks.
Yeah, thanks very much. We also have a question in the chat. It's basically why any insights on why
it's not really the nested condition, it's the nested misspeculation. So the idea is basically the following. So suppose that you have a program where maybe I can annotate here just to say it should be fast. So suppose that you have a program that has this control flow. And this is the right control flow of the program. Well, no, sorry. Let's say, let's do this balance that is easier. So this is the right control flow of the program, suppose. And so now there are many points of misprediction, right? There is this point of misprediction. There is this point of misprediction. There is, so if the processor mispredict, it can go basically in this direction. And then again, at this point, it can either mispredict or can predict correctly, right? So let's suppose that this is the correct prediction, this is the misprediction. So they show that it's enough to look at what happened when you always mispredict. You can skip the case where you basically correctly predict. And this is enough basically to over approximate the leakage that happen if you predict. And the reason is that if the pipeline mispredict in this case, when it will roll back this, will also execute this branch later on, right, for the correct prediction. So there is no need basically to check the condition where you only mispredict 2 branches. You can just check the one where you mispredict all branches.
Yeah, thanks very much.